DC to DC converters. Several industrial applications require power from DC voltage source. Thus, a DC to DC conversion is required. Methods of obtaining variable DC. First one, resistance control. It uses a variable resistance between the fixed DC source and the load to get variable DC or desired DC. And this method used in control of traction motors. Simple method. The disadvantage is power inefficient due to losses in the resistor. Advantage and disadvantage. Second method, motor generator set. A fixed DC is given to motor, then you will be getting mechanical output that will be given to generator desired DC voltage. It requires two machines of same rating. System is bulky, costly, and slow in response. So these are all the disadvantages of this method. Third method, AC link. In this, DC input is given to inverter and the output of the inverter is the AC. This is given to a transformer. It may be a buck or boost, and then this AC is again given to a converter from which you are going to get desired or variable DC. The only advantage of this method is the transformer provides isolation between load and source. The fourth method, the DC to DC converters or DC choppers. Here, the fixed DC is given to DC chopper and you will be getting desired DC. So it directly converts from fixed DC to desired DC as equivalent to DC transformer, we can say. DC choppers, a high-speed on-off semiconductor switch is used. When the switch is off, no current flows. When the switch is on, the current flows. The advantage of using this method is smooth control, high efficiency, fast dynamic response. DC choppers uses the power switches and diodes for the requirement of chopped output voltage. Power switches, power BJT, power MOSFET, GTOS, and source commutator thyristors. As the switch has zero resistance in its on state and infinity resistance in its off state. Switches open and close instantaneously irrespective of the current flowing through them. And the diodes has zero threshold voltage. Diodes has zero forward resistance and infinity reverse resistance. The power semiconductor devices has on state voltage drop of 0.5 volts to 2 volts, due to which the losses in the DC chopper reduces and the efficiency increases and the switching speeds in microseconds. So we'll be getting fast dynamic response and smooth control. It can be used in regenerative braking of the DC motors to return energy back to the supply. And this feature results in energy savings for transportation system. The applications of the chopper: electric automobiles, electric traction for speed control and regenerative braking, in subway cars, trolley cars, hoist and mine haulers. It can be used in DC voltage regulators and current source inverters to generate DC current source by the conjunction with an inductor. Principle of step-down operation of a DC chopper. Consider a circuit with the R load and the switch is nothing but a chopper. The input voltage is Vs and the output voltage is V0. Voltage across the chopper or the switch is Vh. When the switch is closed for time t1, the input voltage Vs is going to appear across the load. And when the switch is open for time t2, the output voltage will be 0. Similarly, the current will be I0 equals to Vs by R. And the current flows when the switch is closed for the time t1. And the current will be 0 when the switch is opened for the time t2. In practice, in practical devices have a finite voltage drop rating of 0.5 to 2 volts. And for the sake of simplicity, we neglect the voltage drop of the power semiconductor device. The average output voltage, V average, is equals to 1 by T integral 0 to T1 T0 dt. That equals to T1 divided by capital T. This V0 equals to Vs. This equals to 1 by T is nothing but frequency F, T1 and Vs. V average equals to K times Vs. The average load current I average equals to V average divided by R, which equals to K Vs by R, in which capital T is known as chopping period, F is known as chopping frequency, and K equals to T1 by capital T, or F of T1 is known as duty cycle of the chopper. Now, the RMS value of the output voltage V0 is equals to 1 by T integral 0 to Kt. Here, this is Kt V0 square dt under the square root, which equals to Vs square of Kt divided by T under the square root. We will be getting root K Vs. Assuming a lossless chopper, the input power to the chopper is same as the output power, then the Pi is equals to input power 1 by T integral of 0 to Kt V0 I dt. This equals to K Vs square by R. The effective input resistance is seen by the source Ri equals to Vs by Ia, that equals to Vs by K Vs by R, which equals to R by K, where K is the duty cycle. As the duty cycle K equals to T1 by capital T, or T1 multiplied by the chopping frequency F, K can be varied between 0 and 1 by varying T1, T, or F. Output voltage V0 can be varied between 0 and Vs by controlling the duty cycle K, and the power flow can be controlled. We have two types of controlling methods. First one, constant frequency operation, in which the chopping frequency F or the time period T can be kept constant and T1 is varied. That is, on T1 is varied. This type of control is known as pulse width modulation control. Second type of controlling method is variable frequency operation, in which the chopping frequency F is varied by keeping turn on time T1 or turn off time T2 constant. This type of control is known as frequency modulation or pulse rate modulation. The frequency has to be varied over a wide range to obtain full output voltage range. This type of control would generate harmonics at unpredictable frequencies, and the filter design would be difficult. The find average output voltage, RMS output voltage, and the efficiency of the chopper, effective input resistance. Now, when you observe this circuit, that Vs equals to the voltage drop across the chopper plus the output voltage. Now, the output voltage V0 will be Vs minus Vch, and the input current I given by Vs minus Vch divided by R. Given data, Vs equals to 220 volts. Voltage drop across the chopper is 2 volts. R equals to 10. The chopping frequency is 1 kHz. Duty cycle is 50. Average output voltage is given by 1 by T integral 0 to Kt V0 dt, that equals to Kt by T of V0, that equals to K of V0 is Vs minus Vch, that equals to 0.5. Since the duty cycle is 50%, 220 volts minus 2 volts, 218 by 2, which equals to 109 volts. Now, the Vrms V0 equals to 1 by T integral 0 to Kt V0 square dt, and the square root of K V0, that equals to root of 0.5 to 20 minus 2 volts, that will give us 154.15 volts. Ri, effective input resistance, is given by R by K, that equals to the load resistance is R is equal to 10 divided by K is 0.5, which equals to 20 ohms. Now, to find out the efficiency of the chopper, we need to find out power output and power input. Now, the power output is given by 1 by T integral 0 to Kt V0 square by R dt. When you solve this, you are going to get K of Vs minus Vch whole square divided by R. Substitute this value 0.5 multiplied by 220 minus 2 divided by R is 10 whole square. P0 equals to 2376.2 watts. Pi equals to 1 by T integral 0 to Kt Vsi dt. To this, then you are going to get K of Vs minus Vch of Vs divided by R. 0.5 multiplied by 220 minus 2, 220 divided by 10. You are going to get 2398 watts as input power. Then the efficiency is equals to the output power, that is 2378.2 divided by 2398, which will be approximately equals to 99%. In the efficiency calculation, we include the conduction losses of the chopper and we don't consider the switching losses due to the turn on turn off of a practical chopper. Then the efficiency of a practical chopper varies between 92 to 99.